Okay, thank you very much. So let me first remind briefly the highlights of the previous episode. So I will do it in a slightly more general form. So our setup is the following. We have a countable space. And we have a Markov chain on this state space determined by the family of the transition probabilities, pi x. And then I call a function to be harmonic. If it has the mean value property with respect to this family of transition probabilities. Now let's assume that our space X is embedded into something bigger, let's say in a topological sense. So somehow we have attached a boundary to our space, or it has been attached to it from the very beginning, like, for instance, in the example I was considering with the homogeneous tree of degree 4, which, as was revealed yesterday, is also the Cayley graph of the free group with two generators. There is a natural boundary, which is the space of infinite words. And now let's assume that the sample paths of our random walk have the property that they almost surely converge to this boundary. Of course, this boundary point need not be the same for all sample paths, so certain sample paths will converge to this point, certain sample paths will converge to another point, and so on. Okay, then here we have, in other words, we have a map which assigns to any sample path its limit point. And now, since we are talking about a Markov chain, we have the associated measure in the space of sample paths, or rather we have a family of measures parameterized by the starting point. Therefore, if we start from a particular point x, then the associated measure in the space of sample paths depends on this point x, and then we can just apply this map to the measure in the space of sample paths, which gives us what probabilists call the heating distribution, or what I will call the harmonic measure. So we have not a single harmonic measure, but a family of measures parameterized by points from our state space. So we have kind of a bundle of measures, and that's precisely what appeared very prominently in the talks yesterday afternoon when talking about Patterson-Sullivan measures or densities. Now, this family of measures, of course, and that's the whole point, they agree very nicely. So in the case of Patterson-Sullivan measures, well, they're mutually absolutely continuous, and their Radon-Nikodym derivatives have a nice geometric interpretation. Here they also have a nice interpretation, but probabilistic interpretation. Namely, the situation is the following. If we start from a certain point x, before reaching the boundary, we have to make the first step. And we can therefore look at our travel from the starting point to infinity in the following way. Okay, we take off from the point x, and then we stop after the first step, and then we continue our movement. And then, of course, because of the Markov property, once we have stopped here, we can forget about all the past. What matters is only the present. So what is Markov property? Markov property is that the present is the only thing which relates the future and the past. So I'm sure it must have better interpretation in more classical texts. Okay, so what does it mean here? That if we start from the point x, we make our first step. We pass to a point y with probability pi x of y, and then we continue our motion to infinity starting from the point y. So it means that our family of harmonic measures, our family of heating measures satisfies this relation, which can be called stationarity relation. And now, all this is very nice and has nothing to do with harmonic functions so far, but they will appear in a second. Why? Because now if we have a bounded function on the boundary, then we can integrate it against this family of measures. And here it comes very convenient, the fact that we don't have a single measure, but we have a family of measures. So we can integrate our test function against each of these measures. And therefore, the result will depend on this index, which we have put here. And now this stationarity relation immediately implies that the function f, which we have obtained this way, is actually a harmonic function. It satisfies the mean value property. Because here the stationarity is nothing else than a mean value an averaging mean property for the family of harmonic measures. Okay, so if we have boundary convergence, then it gives us a harmonic function. Now, conversely, if we are given a harmonic function, then we can also exhibit a certain boundary behavior just in terms of this harmonic function. How do we do this? Let's look at the sequence of values of the harmonic function along sample paths. So let me denote it. I will use the capital F to consider this as a, okay, I should put F sub n here, as a sequence of functions on this space of sample paths. Okay. And now harmonicity means precisely that this family of functions Fn is a martingale. With respect to the increasing sequence, increasing filtration of the coordinate sigma-algebras. So this is letter A. And here I put subscript 0 and superscript n. So this is the sigma-algebra generated by the positions of our Markov chain at times between 0 and n. Okay, so I don't really have time to remind the definition of a martingale. That's really also a mean value property, and averaging property. But what I need here is the following fact, the famous martingale convergence theorem. Namely, if we have, let's say, bounded martingale, then it converges almost surely. So in our situation, it means that our harmonic function is almost surely convergent along almost all, is convergent along almost all sample paths. Okay, and therefore, we have two types of boundary behavior. So one comes just from geometric considerations. So here we have a certain a priori boundary, and then somehow we know that our sample paths do converge to this boundary. So here one has to know something about our Markov chain in order to be able to establish this convergence. So this is one type of behavior at infinity, and this is another type of behavior at infinity. But here we don't have any geometric boundary. So the only thing which we have is a bounded harmonic function. And still, by looking at these limits along sample paths, we can distinguish between different sample paths by looking just at the behavior at infinity. So how can one combine these two descriptions of non-trivial behavior at infinity? Actually, they turn out to be essentially the same. So let me do it in more rigorous terms. So here I have my space of sample paths. That's a space of all sequences of points, which I denote x bar. And then this space is endowed with family of measures corresponding to various initial points. So here the subscript is initial point. Or more generally, one can also consider measures determined by a given initial distribution theta, just by taking the corresponding weighted sum of these ones. Or an initial distribution theta. Okay, and I have already mentioned, and technically one can, for instance, take a certain reference initial distribution, which would just charge all the points from our state space to make life easier. And now I have already mentioned a certain family of sigma-algebras here. That's the coordinate sigma-algebras. And now I will introduce another sigma-algebra, which I will denote by E, and I will call it the exit sigma-algebra. And this sigma-algebra, actually, I will describe it. I cannot say that it is generated by certain random variables. Rather, I will describe the events which are in this sigma-algebra in a different way. So here one can consider the following equivalence relation. Suppose that we have two sequences. Let's say x naught prime, x1 prime, and so on, xn prime. I want to define a certain equivalence relation which will tell me that these sequences, which will tell me when these sequences have the same behavior at infinity. Okay, so how do I do this? Suppose that I have a convergent sequence, right? Then you know that if I have a convergent sequence and if I replace any finite number of enters, it's still convergent, and it converges to the same limit, right? Or, moreover, if I have a convergent sequence and I shift it, then it is also still convergent, and it's convergent to the same limit. Okay, so that's very, very natural assumptions, and more or less clear, it's more or less clear that if I want to talk about the behavior at infinity, then, of course, this behavior at infinity should be preserved under these elementary manipulations with sample paths. So if one is obtained from another one in this way, then they should still have the same behavior at infinity. So what is my equivalence relation? It's the following, that there exists a pair of indices, n and n prime, such that, okay, so let me put it here, xn, and here it will be xn prime prime, such that starting from these two indices, the trajectories will just coincide up to the shift. So they are not synchronized. N and n prime can be different. So xn plus I is equal to x prime n prime plus I for all i's greater or equal than 0. So this is obviously an equivalence relation on the space of sequences, actually. I don't even have to know that they're sample paths of something. And now I want to make a sigma-algebra out of this equivalence relation. And of course, I cannot say that my sigma-algebra will consist of unions of these equivalence classes, because there will, of course, be very wild unions like that. But instead, I should say that my sigma-algebra consists of measurable unions of equivalence classes. Or in other words, this is what is called the measurable envelope of this equivalence relation. So it's easy to say, but as we'll see later, actually, it's not so easy to understand, for instance, whether this sigma-algebra be trivial or not. But from the abstract point of view, that's very easy and natural definition. Okay, so this is what I call the exit sigma-algebra. And now the claim is the following. The claim is the following, and then, yes, since now I have started to talk about sigma-algebras and measure spaces, of course, I should recite the usual incantation, and I should say that from now on, everything happens in the measure category. Namely, everything is considered modulo 0, modulo subsets of measure 0. So in particular, this sigma-algebra actually, it's also has to be what is called complete. Namely, it should also contain all the subsets of measure 0. So that's a standard assumption. Okay, and now the claim is the following. Due to David Blackwell in 1955, that the space of bounded harmonic functions, well, here maybe I should specify that this space depends not only on our state space, but of course of the transition probability. So I will put here P, which stands for the Markov operator of my chain. Okay, so it's more or less the same as the collection of the transition probability. So the space of bounded harmonic functions is diametrically isomorphic to the space of all measurable functions on the path space. Well, here I have to put a certain measure. As I said, the easiest will be just to take a reference initial distribution which charges the whole state space, so that all the other measures will be absolutely continuous with respect to that one. And finally, here I need one more ingredient, which is the Sigma-Algebra, which I have just defined. So here in the right-hand side, this is just a space of all measurable bounded functions which are additionally measurable with respect to the exit Sigma-Algebra. Okay, so how does one prove this theorem? Very simple, and essentially I have more or less already outlined the proof. The proof is the following. So suppose that I have a bounded harmonic function. Then we know that our bounded harmonic function, its values, converge along almost every sample path. Therefore, this limit is a certain measurable function on the space of our sample paths. So let me denote f hat of x bar. So x bar is our sample path. And here, by the very definition, this function f hat is a limit. And therefore, as a limit, it will survive, it will keep its values under, if we replace a sample path with another sample path which is equivalent, because they will just coincide starting from a moment, therefore the limits will be the same. So this function, therefore, belongs to this space L infinity. This function belongs to space L infinity. Okay, and in the opposite direction, well, this is how one does it in the martingale theorem, because if we have the martingale limit, then the martingale can be recovered by taking the conditional expectations of the limit function. So in this situation, it means the following. So if I take a measurable function on the space of measurable with respect to the exit Sigma-Algebra, then I will define function f as the expectation of the function on the space of sample paths with respect to the probability measure associated to my starting point x. So, well, at least this formula makes sense. This formula makes sense. So here, what one has to verify, of course, one has to verify that the resulting function is harmonic. So I have written the definition. One has to verify that it is harmonic. But this is where one will use that this is not just an arbitrary function, but that's a function from the exit Sigma-Algebra. Okay, so that's, I will keep this part, so that's relatively simple. And then this is what had been done by Blackwell. And Blackwell actually, here, I'm not sure he was thinking about the Poisson formula, which is very much similar to what we have here. And at the moment, we'll see that this is precisely the Poisson formula. However, there were other people, and they were all more or less founding fathers of the modern probability who thought about this. So it was Feller who was thinking about this simultaneously with Blackwell, and he was actually very much inspired by the Poisson formula. And for him, unlike for Blackwell, who was a probabilist, so it was perfectly okay to leave his result like this. It's really a very short note. It's only 4 pages. So Feller, okay, maybe he had a deeper background. wanted to have something similar to the classical Poisson formula. And the difference between what we have here and what we have in the classical Poisson formula is the following. In the classical Poisson formula, we have a boundary space, which is really a certain topological space, so you can touch every single point of this space. And then, well, you can take continuous functions on this space, or maybe even not only continuous, but just measurable. But anyway, you can also touch these functions with your hands. And then, well, you integrate them, and you obtain your harmonic function. Whereas there is no space. We just have a Sigma-Algebra. We just have a Sigma-Algebra, and this really puzzled him. And, well, one can define a topological space just starting from a Sigma-Algebra. That's essentially the, well, certain Stone-Check compactification, Stone-Check compact, and he described it in a pretty technical way. Then there was several other people working on this subject, among whom, for instance, Doob. But still, it was not clear. All of them still wanted to have, as Kendall also worked on this, so all the founding fathers. It was not really nice to obtain these topological spaces. Then there came Furstenberg, and Furstenberg, his inspiration was really the Poisson formula, because he was interested in semi-simple Lie groups and in harmonic functions on the associated symmetric spaces. And there, of course, there is always, even in the higher rank case, there is very nice topological space. And he wanted to have such a topological space, but obtained from abstract considerations. And therefore, he introduced what was called by himself, well, he couldn't call it Furstenberg boundary, but actually, this is what people working in symmetric spaces now call the Furstenberg boundary, the space of flags, by also a certain, still pretty complicated construction. However, it turns out that the right answer here is the following: one can still have a space, which will provide us with a Poisson representation formula, not just a Sigma-Algebra, but a space. However, the point is that the space shouldn't be considered or treated as a topological space. It should be considered as a measure space with all the associated advantages and disadvantages. So what are the advantages? Advantages are that in the measure category, as I said, you can discard subsets of measure zero. So if you have just a countable set of fixed points or anything, you don't care about them. So that's definitely an advantage. The disadvantage is that in a measure space, it's kind of difficult, once again, to feel what are the individual points, because as I have just said, you can throw away any single point, and then what is left? Well, still, what is left is a measure space. Now, here I have to remind a construction which is commonplace in the ergodic theory, but unfortunately pretty much unknown to probabilists, which is a shame because, well, actually, the whole state of teaching measure theory, I think, is completely unsatisfactory because if one asks someone who listened to a standard course of measure theory, suppose you consider the unit interval and the unit square. Are they the same measure spaces or not? This question is actually never asked. So you have squares, you have intervals, you have cubes. Each of them is its own measure space. Why would one compare them? But in fact, actually, all these spaces are the same. All these spaces are the same, and that's the central point of the theory of Lebesgue measure spaces. Or sometimes they're called Lebesgue-Rochnin measure spaces. Or sometimes they're also called standard probability spaces. So essentially, this theory of Lebesgue spaces tells us that there is actually only one measure space, only one nice measure space, which is the unit integral. And maybe if you don't want it to be so nice, you may add a certain countable number of atoms. So that's all measure spaces there are. Well, of course, reasonable measure spaces. I really want to go into details here, but I will just say that the standard example, standard class of topological spaces which produce nice measure spaces, so they are wildly different as topological spaces, but as measure spaces, they will all be exactly the same. If one has a Polish space, so it's separable, metrizable, complete, endowed with the Borel sigma-algebra, then any measure on this Borel sigma-algebra makes it a Lebesgue space. Makes it a Lebesgue space. So now here there is a subtlety because, of course, the Borel sigma-algebra comes from the topology on this Polish space, but once I consider it in the measure category, I inevitably have to complete my sigma-algebra by adding all the subsets of measure 0. Then this sigma-algebra becomes much, much bigger than the Borel sigma-algebra, but what we acquire is the independence of the topology. So what we obtain is just, if our measure is fully non-atomic, is a measure space which will be just isomorphic to the unit interval. Okay, so now it turns out that in the category of Lebesgue spaces, it is not only, one can classify not just Lebesgue spaces, but also, if talking in categorical terms, one can also describe all the morphisms in the of Lebesgue spaces, and there the description is also very, very simple. So the model situation is that if one takes a unit square endowed with the Lebesgue measure and projects it onto the horizontal interval. So that's, well, we have one probability space and project it onto another one. And then it turns out that once again, assuming that we don't have atoms anywhere, any homomorphism of between Lebesgue spaces has this form. Any homomorphism between Lebesgue spaces has this form. Question? Okay, and now what do I need? I need one more very nice property of Lebesgue spaces. That's one-to-one correspondence. Between complete sub-sigma algebras and quotient spaces. So what do I mean here? The following. So suppose that we have a quotient of our measure space. So this is an example, and this as I have just said, is actually the general case. Then one can look at the associated preimage sigma algebra. So we take measurable subsets inside the quotient space and look at their preimages. So this will be the corresponding kind of cylinder sets. Okay. So in this case, the sigma algebra determined by this projection is just a sigma algebra of all vertical sets. One can call them vertical sets. Okay, so in one direction it's obvious. If we have a quotient space, then we have the associated pre-image sub-sigma algebra. And now a fundamental fact about Lebesgue spaces is that this correspondence is actually a bijection. Namely, conversely, if we have a sub-sigma algebra, no matter of what origin, then necessarily it comes from a quotient space. It comes from a certain quotient map. And now this is precisely what I'm going to apply in this situation. Because we have a measure space, which is the space of our sample paths, and we have a sub-sigma algebra. We have a sub-sigma algebra. And then I can just quotient my space in such a way that this exit sigma algebra will be realized as the preimage sigma algebra of this quotient map. So it is the resulting quotient space which is called the Poisson boundary. The quotient of the path space determined by the exit sigma algebra. So this is a measure space. This is a measure space, so I will denote it actually also by dx. Maybe here I will put capital P, which stands for my Markov operator for the collection of the transition probabilities. It is endowed with the family of measures parameterized in the same way as the measures on the path space. So if we start from a certain initial distribution, we take the associated measure, we quotient our space, and then the resulting image measure is what's called the harmonic method. So here, in particular, if we start just from a single point, then the image of the associated measure in the path space, when we project onto the Poisson boundary, will be the corresponding harmonic measure. And now I can return to the Poisson formula of Blackwell, and I can now write it in terms of the Poisson boundary, And then it becomes precisely the same. It will be described by precisely the same formula as the classical Poisson integral. So, what is the correspondence then? If we have a bounded measurable function on the Poisson boundary, okay, so here I write nu in square brackets because I don't really need the any individual harmonic measure. I just can take the maximal measure class of these quotient measures. So if I have a measurable, bounded measurable function on the boundary, then I associate to this function the harmonic function on the state space, defined in the following way. Its value at a point x is just the integral of the boundary function against the corresponding harmonic measure. So that's precisely the same formula as in the classical Poisson integral, but now given a different interpretation. Yes?
How much probability is the quotient that work with the space of paths with the Sigma-Algebra instead?
I'm a probabilist. Yeah. Oh, okay, the difference is the following. So you really want to have a space, for instance, in order to be able to talk about quasi-invariant measures. Moreover, it's actually very convenient to talk about these points of this measure space. Well, they're not individual, but still they're defined almost everywhere. For instance, if you have a point, then you can talk about, well, what's the difference between these two approaches in general? So that's like the difference between having conditional expectation and having a family of conditional probabilities. So, of course, if you just want to integrate, you don't really have to care about conditional probabilities. You can always write the conditional expectation. However, in certain situations, it is really necessary to talk about the conditional measures. And in particular, in this context of Markov chains, if we have our Markov chain, then it makes sense also very often to condition this Markov chain at infinity, to choose a boundary point and to consider the corresponding conditional measure. So this will be also a certain Markov chain, but with the property that it converges to the corresponding boundary point. So, yeah, maybe let me give one example how it works. So just why it is interesting. So let's take once again our free group or homogeneous tree, and here we consider the simple random walk. So I don't even want to describe it in group terms at this moment, so just we have simple random walk. The transition probabilities are 1/4. And then we have the family of boundary measures, which in this language, they also coincide with the family of the Patterson measures. The family of the Patterson measures, and why do they coincide? Because their Radon-Nikodym derivatives are very nice. Namely, suppose that I have two points which are neighbors, say x and y. Okay? And now this is very convenient description, because I can actually write it like this. We have x, y, and then one part of tree growing from x and the other part of tree growing from y. Okay, and now let's look at the boundary first from the point x. Okay, so here, for instance, each of these branches has the weight 1/4, right? But now, if I go one step back and I look at the same piece of the boundary from the point y, then I will zoom out, actually, the picture. So now each of these branches will only have the weight 1/12. So that the ratio is 1/3. The ratio is 1/3. Okay? On the other hand, if I'm looking from the point x at this part of my boundary, then if I make one step closer to this part, then I will see better. And this magnification coefficient will be also a power of 3, but now it's not 1/3, it will be 3. Okay, so these Radon-Nikodym derivatives will be actually just power of 3 arranged in a very nice geometrical manner. so that one can say that the Radon-Nikodym derivative will indeed be, Radon-Nikodym cocycle will be indeed the exponent of the Boseman cycle. Okay, so now here, what are the, I will explain it later, but actually it turns out that if we, in this particular case, if we consider our boundary as a measure space endowed with the family of these heating measures, then it happens to be the whole Poisson boundary. It happens to be the whole Poisson boundary. Okay, and so now, as I have promised, what happens if I condition my random walk to end up at a certain particular boundary point? So the Poisson boundary, as I have said, is the set of all infinite words of all the ends of this graph. And now I fix one of them. And of course, I shouldn't say that because one cannot condition with respect to a single point. It has probability 0. But that's precisely what I was talking about. That's where I need the family of the conditional probabilities. So these conditional measures will exist almost everywhere. And now what will be these conditional probabilities? Actually, as I said, they're very nice because they're not just certain weird measures on sample paths, but they themselves, they also correspond to Markov chains. What do we have to do? We just have to take the original transition probabilities and modify them by multiplying by the same exponent of the Boseman cocycle, by the same magnification coefficient which we have here. So what does it mean? Here the transition probability for the unconditional chain, it was just 1/4. But now we have to multiply the 3/4. Why do we multiply it by 3? Because that's the direction which goes to where we want to end up. And why by 3? Because 3 is actually precisely the Radon-Nikodym derivative of the corresponding harmonic measures. Okay, now if I go to any of the 3 remaining points, then all of these points will be further from final destination. And therefore here the value of the Boseman cocycle will be 1, or will be -1, and therefore the value of the corresponding Radon-Nikodym derivative will be 1/3. And therefore here the transition probabilities will be 1/12 each. And one can directly check that there are still transition probabilities because the sum is still equal to 1. Sum is still equal to 1. So that's why it is much more convenient and much more informative to have not just the Sigma-Algebra, but also the associated quotient space. Okay, so now what do I want to say? Now the problem is the following. The problem is the following, and I have actually already touched this problem. The problem is the following. How does one identify the Poisson boundary? And particular case of this question is the following. When is the Poisson boundary trivial? What does it mean trivial? It means that it consists of a single point. So that's also a particular case of this identification problem, except for in this situation, we want to identify the Poisson boundary just with a single point. When is the Poisson boundary trivial. Okay, so what does it mean that the Poisson boundary trivial? Well, one can give an answer which is not fully satisfactory in terms of harmonic functions, because we know that the Poisson boundary is responsible for describing the space of bounded harmonic functions. And therefore, if here we just have one single point, then there is nothing to integrate, and we will always obtain just a constant. Therefore, triviality of the Poisson boundary means the absence of non-constant bounded harmonic functions. No non-constant bounded.
Is this the gradient of the Gaussian function?
Sorry?
The variables that you've written there, is that the gradient of the Gaussian function also?
Okay, no, the, how shall I put it? No, the gradient of the Buseman function will be plus and minus 1 on a graph. Yeah, so here, what I take actually 3 to the power beta. And this will be the Radon-Nikodym cocycle. Okay, let me write this formula in full. 3 to the power beta gamma of xy is, well, that's actually the formula which was written okay, and here I'm never sure whether I should put minus here or plus. Well, depending on the definition of the Buseman cocycle. Okay, so triviality of the Poisson boundary means that there are no non-constant bounded harmonic functions. Or it is called the Liouville property. The Liouville property. Okay, so now let's return to our previous examples, and let's see what we have in terms of the Poisson boundary. Okay, so we had two basic examples. One was this, let's again say, homogeneous tree. Okay, so here we actually have boundary convergence, which provides with certain behavior at infinity. But then the question is the following. The fact that here we see convergence of our sample paths to the geometric boundary doesn't necessarily mean that what we see is the whole behavior at infinity. So that's like in any area of mathematics. So suppose you are asked to describe the complete system of invariance of a certain object or whatever. Then, of course, you may see certain invariance immediately. But then sometimes it's easy and sometimes it's not so easy to show that there is nothing else. And sometimes it may be not true, meaning that you didn't look well. Okay, so in this case, the question is the following. Is the observed boundary the whole Poisson boundary? Okay, and now the other case was, well, actually I only did it in the one-dimensional situation for the random walk on the integer line, but let's say, let's consider the plane. And actually here it's not as obvious as it was on the integer line. So this is also a graph. That's also a regular graph. Each point has, each vertex has 4 neighbors, so that we can consider simple random walk. It will have the same transition probabilities, 1/4 to any neighbor. But The point is that here we don't really see any boundary behavior. Well, sample paths, they look quite complicated, but still there is no way to measurably distinguish one collection of sample paths from another collection of sample paths by looking at how they behave at infinity. So what is our candidate boundary? The candidate boundary is just a single point. A single point. So what we have to do in this case, we have to show that indeed the fact that we were not able to produce any boundary behavior doesn't indicate that we are not smart enough. No, it does indicate that we are smart. It indicates that indeed the Poisson boundary is trivial. Is the Poisson boundary trivial? Okay, so that's okay, and I have about 20 minutes, right? Okay, so far, actually, I haven't, well, I did say the word group on several occasions, but in principle, all this theory doesn't require the presence of any symmetry. So all this is valid for an arbitrary Markov chain. For simplicity, for technical simplicity, I was assuming that the state space is countable, but by making various reasonable assumptions, one can also extend this theory to continuous state spaces. And now I'm going to impose a new assumption. Now from general Markov chains, I'm going to pass to random walks on groups. So these are actually an extremely natural class of Markov chains because they can be characterized as Markov chains which are homogeneous both in time and space. Well, actually, I didn't consider Markov chains which are not homogeneous in time, but it's possible. It would just mean that transition probabilities depend not only on the point where you are, but also at the moment of time. Okay, now this is time homogeneity, but now I can consider also homogeneity in space. So chains homogeneous both in time and space. So what does it mean? Well, I have then to specify what homogeneity in space means. And as usual, it means the presence of a certain symmetry, the presence of a certain group action, or in the simplest case, just the action of the group on itself. So now I'm assuming that my state space X is a countable group. And I want the transition probabilities to respect this group structure. I want the transition probability to be homogeneous in space. So what does it mean? Who are transition probabilities? So one can think about them as little clouds attached to each of the points of the state space. Okay, then homogeneity means the following, that we have a cloud over the identity of the group, then the cloud over any other point, G, has to be precisely the translate of the cloud which was about to reign over the identity. So who are these clouds in more formal way? They are transition probabilities. So in other words, now I want that everything be determined just by the transition probability from the identity. So let me denote it by mu. So that's a probability measure on the group. And then what I want the transition probability from a point G to be the corresponding translate of the map U. Or in other words, my Markov chain has very simple interpretation. No matter where you are on the group at any point G, what you do is the following. You take an increment sampled from this step distribution U, and you multiply, let's say on the right, let's consider the right random walk. That's how I consider the action. And then we multiply our position by this increment on the right. So in particular, if I start from 0, from the identity of the group at time 0, then the position of my random walk will be the product of, in probabilistic language, of n independent identically distributed random variables, which are the increments at each step of the random walk, because they're all sampled from the same distribution mu. So usually when giving this definition, then one gives the famous example of Poisson. And usually first one makes it one-dimensional, because that's what one can do with one coin. Then, well, if you are lucky and you have 2 coins, then there is more variety, so you can choose out of 4 direction. Then one can walk on the 2-dimensional lattice, and then one really has to make an effort to convince people why ever one should consider non-commutative operations. Why should one ever consider non-commutative groups? However, the reality is that the model, this model of random walks on groups was actually first introduced not by Poisson. It was Poincaré and Hadamard. Who almost simultaneously with Markov, there is just 2 or 3 years gap between them, were considering the model of card shuffling by sending their greetings to Percy Diaconis. And there is a description of the resulting probabilistic model of the Markov chain of the random walk on the symmetric group, which appears in Poincaré's course of probability in 1912. At that time, the work of Markov wasn't apparently known in France yet, although he had published something in a German journal, and it was a part of the German translation of his work. But yeah, there is no doubt that at that time they were not aware of Markov. And well, one has to say that Markov considered a model, well, which is very simple to explain. He considered how the dependencies between letters in various texts. So there are no groups there by far. Whereas Poincaré, from the very beginning, considered really the random walk on the symmetric group, on the group of permutations of n elements, of n cards. And the way he defines it looks actually very surprisingly modern. So when someone writes a paper on random walks nowadays, one actually uses precisely the same words that Poincaré used more than 100 years ago. Namely, one is given a group and one given a probability measure. Maybe he denoted it by P, not by mu, but that's the only difference. And then, of course, for him it was obvious that the group of permutations is a non-commutative group. Okay, so now I have formulated this setup. Now I can repeat the same general questions, That's the question about the identification of the Poisson boundary and about its value. But now I can do it in a more specialized environment. So now the setup is the following. G is a countable group. And mu is a probability measure on this group. Then I reiterate these two questions. So first, identify the Poisson boundary. So I will denote it like this. So that's a boundary with subscript mu, because it really does depend on the measure. By the construction, let me make this comment here. So everything here is defined in the measure category only. And there, how did I obtain my Poisson boundary? I took the path space, and this path space as a probability space depends on the transition probability, on the step distribution, and then I somehow quotient this path space. Now, if I take another measure on the same group, then of course it may so happen that it is somehow related to the original measure. For instance, I can take the convolution power of this one. Okay, in this situation, the path spaces are naturally related. But if I just take an arbitrary pair of measures, then there is just no way to compare these boundaries. Okay, so the presence of the measure here is very important. Okay, so the first question is to identify the boundary, and the second question is to decide when this Poisson boundary is trivial. So that's a particular case of this identification problem. So now maybe let me give a couple of examples of what one can actually expect on groups. What are the typical behavior which is described by the Poisson boundary. So here our knowledge is actually still quite limited. The number of examples for which Poisson boundary is explicitly known is very limited. It's still within, let's say, 12. And essentially there are two types of boundary behavior which have been known until very recently. I'm saying until very recently because now there is yet another example, another type of the boundary behavior, which I will hopefully describe in the forthcoming lectures. But the two types which had been known before are the following. So types of boundary behavior. The first one is, I can call it, let's say, hyperbolic boundary behavior, which is the following. We have already seen this. So here our group looks like a word hyperbolic group, these conditions can be relaxed in various directions, but one should really think just maybe about the free group. Here, what we have a well-defined geometric boundary of the group. We have a well-defined geometric boundary, and it is in terms of this geometric boundary that we want to identify the Poisson boundary. So here, typically the sample paths will converge to a point at infinity, which is usually not very hard to establish, like what we have seen in the example of the simple random walk on the free group. So there, the boundary convergence wasn't really a problem. But what is much less obvious is verifying that this boundary behavior is indeed everything what can happen. So the question is whether the observed boundary is indeed maximal. It is the whole Poisson boundary. And here, well, there are positive results and there are open questions. So the positive result is that under reasonable moment conditions, one can indeed identify the Poisson boundary. That's a reasonable moment conditions. Yes. However, surprisingly, and this identification works not just for the free group, but for a pretty wide family of groups, hyperbolic groups, discrete subgroups of higher rank groups, mapping class groups, relatively hyperbolic groups, and so on. But all these situations require a certain restrictions on the measure, like finite first moment. In the general situation, here I have to put very bold interrogation mark, because here the answer whether the infinite words indeed describe the whole Poisson boundary for an arbitrary measure is unknown even for semigroups. Even when there are no cancellations, and that's really a shame, even when there are no cancellations, we don't know how to show that there is no other boundary behavior than the infinite word. In other words, probabilistically, it means the following. One has to show that given an infinite word, so if we are talking about free semigroup, there are no cancellations, so it's just concatenation. We have random words and we put them next to each other. We obtain then an infinite word, and the problem is to show that there are no essentially different ways to decompose this infinite word into these increments. And surprisingly, this is not known. Okay, so now there is another type of boundary behavior which is configurational boundary behavior. But I think my time is out for today, so I will continue then tomorrow. Thank you. Yes.
Reasonable moment condition for hyperbolic group. So what is expected that if you have an infinite, you choose an infinite set to be your generating set? So the question that you asked.
Yes.
Under what conditions is the boundary not?
No, here the conjecture is that it is, I find it hard to believe that there will be something else than infinite words or just the hyperbolic boundary, but the problem is that we don't know how to prove it. Yeah. So, but here I don't think there would be much difference between doing it just for a free group, or actually even just for a free semigroup and in the general hyperbolic case. So, and here, that's really a shame. That's such an obvious probabilistic question, and there is something we don't understand.
Is there a reasonable question about realization of the boundary? So if I give you a backspace and count maybe measures, can you construct Markov chain?
Okay, well, no. In the first place, the Poisson boundary, okay, so I should have said more about this. So what kind of structure do we have? So here, yeah, I said that it is a measure space. So it's endowed with a probability measure, and that's a probability measure which one should think about I should think of as the hitting measure from the identity of the group. Okay, so this measure has to be, in the first place, it has to be what is called mu stationary. And that's precisely the stationarity condition which I had already introduced for general Markov chains. So here, since everything is equivalent with respect to group action, it just means that the harmonic measure has to be equal to the average of its translates. Okay, so it is this condition which guarantees that the Poisson integrals will be harmonic functions. And then, well, there are certain other conditions. So that to begin with, what one has to talk about is not a Lebesgue space. We need really an action of a certain countable group. We need the action of a certain countable group on a Lebesgue space, yeah? Well, this countable family will be just a family of translates. So G nu is the same as nu G, yeah. Yeah, so here we have the group structure, so it doesn't make sense to talk about a countable family of measures. We can talk just about one measure and then just move it around by the group. Huh? Yes, that's what I did, yes.
But in that sense, you go back from Poisson boundary, constructing a Markov chain?
Okay, if I have, well, it depends really, because here you see, you are saying, suppose we are given a Lebesgue space, but we know that there is only one Lebesgue space. So it indicates somehow that you have in mind something else that you are not telling us, that you're having in mind some additional structures in this Lebesgue space. Okay. So, okay. So we have countably many measures, and then we want to find an action for which these measures will be the translates of of one of them. That's a legitimate question, yeah. That's a legitimate question. Okay, in this way, it's kind of, yeah, that's a good question, because from this point of view, I don't think anyone looked at it. What one can do, and which is a well-trodden path, It is well known that actually when we are talking about ergodic theory of group actions, we don't really need those actions. We can replace them with equivalence relations. But if you are just given a family of measures without even any equivalence relation, then yeah, one has to think about it. Okay, thank you.